So thanks, Rich. Hi, everyone. I guess you can now see my screen. And what I'll be discussing for the next 15 minutes is how we're trying to build a stack for climate services on top of Xarray and OGC Standards. And for those of you who are not familiar with climate services, I'll just start by giving a short definition. We're basically translating historical and future climate information, so climate projections, historical observations, into actionable information. And what I mean by actionable is that this is information that can be used by decision makers to, for example, engineer infrastructures, decide on urban planning, assess risks, and so on. And so, for example, if you're building a road and you want it to be to offer the same level as service in 25 years than it does today, you need to design it so it can withstand future extreme rainfall, so it doesn't wash away. And so my job and the job of my colleagues is to gather information about future climate conditions and package it so it's useful to engineers and urban planners and researchers from other disciplines that are not climate experts. And we're not alone to do that. Where I work, there's a couple of climate service centers in Canada. So the one I work for, Ouranos, is based in Montreal, Quebec. There's another one in Victoria, BC, called the Pacific Climate Impacts Consortium. There's another one in the prairies called Climate West, and an upcoming new hub in the Atlantic provinces that should be announced in the next few months. At the national level, there's the Canadian Centre for Climate Services, which is a division from Environment and Climate Change Canada. And their job is to essentially coordinate the work of Regional Climate Service Center and offer these types of services to provinces and territories that don't have regional centers themselves. So I'm not so familiar with the situation in the US. I think there is something that is somewhat similar by NOAA. It's called RISAs, so the Regional Integrated Science and Assessment Programs. And so there's a bit over a dozen regional centers that provide that same kind of information, so to stakeholders and decision makers. But my point, I guess, is that every one of these regional climate service center, whether it's in Canada, the US, Europe, or elsewhere, basically have to solve the same issues. They have the same challenges. You usually need to select and subset data, so from observations, from models, and so on. Then you need to subset, regrid, interpolate, average that data over some spatial boundaries, do some statistical bias adjustment to fix model biases compared to local observations. You then compute climate indicators, so it could be degrees of warming, forest fire indices, drought indices, and so on. And then compute ensemble statistics, robustness metrics to evaluate the confidence we have in the results. And then there's visualization, of course. And so when if we want to collaborate on a large scale on developing those kinds of services, my sense is that we need shared principles. And for the data world, they already have a kind of nice set of principles called the FAIR principles. So FAIR for findable, accessible, interoperable, and reusable. And my sense is that we kind of need to translate those principles to the world of services. And the question is, how do we translate what FAIR means, but for not data, but for services? And so, we can make a few guesses. I would say that findable would stand for public catalogs of documented analytical processes. Accessible would mean that those services are available to end users with low bandwidth connections, small CPU and storage. Interoperable would mean that the input and output data are using standard data formats, and the API is a standard API, so everyone uses basically the same conventions. And reusable would mean that this infrastructure is built on open source software. It has rich metadata and tracks provenance information as you run processes over data. And so this is just, my thoughts. I'm sure we can improve on that. But my guess is that the climate science community is really well positioned to do that because it already has agreed on a common set of data format with NetCDF and metadata convention with the CF conventions. We have, I think, the groundwork done. And there's also an existing federated data distribution architecture that's already working, the Earth System Grid Federation. And I mean, we could just simply think of slapping a layer of services onto the data. And so we're trying to build that kind of stack with those FAIR principles that would provide climate services to end users. And how it looks is a bit like this. And to be clear, this is not an effort that's done entirely by Ouranos. It's a fairly large scale community effort with colleagues in Montreal, but also in Germany and the UK and the US. So yeah, take it as the result of a large community effort. And so the stack is based with, it's made of a very thin user interface. It's basically a Jupyter interface or a programming environment. I mean, we've tried in the past to do a graphical user interface, but it was, I mean, a fairly big waste of time, if you want my opinion on that. And so we're leaving that problem to other people. We're really focusing on the back end where the data and the services live. And so on the left-hand part, you see the data components. There's a data catalog. It's currently based on intake, but we're hoping to move to the stack specification, so the spatiotemporal asset catalog. This catalog exposes NCML views of NetCDF data, so I'll come back later on what that means exactly. And so we have a thread server that's hosting and serving this data, and a geospatial data server as well. So GeoServer that exposes, for example, administrative boundaries, watershed boundaries, and so on that we can use to subset climate data. So that's the data component. On the right-hand side, you have the services component. So we have subsetting, regridding services, bias adjustment services, climate indicator services, and many others. And the idea is that the client sends requests, so HTML requests, to either data servers or service servers and gathers the results back. And we can chain different services together to make fairly complex workflows possible. And the way we've built that is essentially by stacking different layers together. So we have this data layer with NetCDF data, CF conventions, and these NCML aggregations. We have the science layer with Xarray and Dask and a whole lot of different scientific libraries. And then we have the service layer where we have a client server implementation based on OGC standards. And so I'll just discuss briefly about what we do in those three layers. So for data, as I said, we have a threads NetCDF server, but we've put on top of that an NCML layer. So NCML is an XML language, if you wish, that allows the servers to collect different individual NetCDF files and present views to those multi-dimensional, basically, data sets. So for example, you could take multiple time slices, multiple variables or ensemble members from the same model that all share the same coordinates and say, this is going to be one single view in our catalog and thread server. So instead of a search returning thousands or tens of thousands of files, you only get a couple of them for each realm and each model and each experiment, for example. And so this drastically, that really reduces the number of items in the catalog and makes it simpler for users. This NCML view also lets you change metadata and data on the fly without changing the underlying binary files. So if there are errors in the dimension names or the units or whatever metadata is in the NetCDF file, you can fix that in the NCML layer. And this lets you kind of have a data as code approach where these NCML files are stored on a Git repo, and you just deploy them on a thread server. And so you can change the views that you provide to users pretty rapidly. So that's one aspect of the data layer. For the science layer, we have different items. I won't go through all of them. I've picked two. One is Xcsmf, which is a community library that wraps the ESMF library in an Xarray wrapper. And so we're using it heavily. And so we're really grateful for the community effort in building this. There's a couple of neat algorithms for regridding. So bilinear, nearest neighbor, patch, and conservative, which preserves the integral inside an area. There's also masking support, and we've recently added support for polygonal averages. And it's really, really fast as well, so it's great to use that. Another science component is Exclam, so that's something that we've developed in-house. It's mostly geared toward climate indicators, so fire weather indices, cooling degree days, heating degree days, name it, there's like over 50 of them. We've started implementing bias adjustment algorithms, so mostly quantile mapping methods for those who know this stuff. We have some utilities for frequency analysis, for example, computing the return period of extreme events, to do some ensemble analysis, and a whole bunch of utilities to deal with different model calendars, missing data, criteria, units, conversions, and so on. And so that's the main science component that we're using, again, all based on Xarray. And the last part is the services component. And so this is what essentially wraps scientific services into web services. And this uses the WPS standard. So that's an open geospatial consortium standard called Web Processing Services, and describes how clients can request services from a remote server. And so the implementation is based on PyWPS, and we have a client called Birdie, which you install on the client, obviously, and communicates with the PyWPS server and provides a user-friendly interface to remote services. And all of this is built into Docker containers, so we can basically spin up an infrastructure fairly easily by launching threads, GeoServer, these services inside Docker containers, and with Docker Compose, bring all of that together. And so just to give you an example of how this works from a client perspective, here is just a small demo. We're importing the WPS client, connecting to the remote server. And this client creates a kind of mock module where all the remote services are presented as functions in this module. So you see different indices here. There's subset functions that are available. And what I'll do next is pick the average polygon service. So that's something that runs remotely on a server, but we've created a kind of doc string based on the information that the server provides. And so this function takes an NCML resource and a shapefile and computes the average of the netcdf over this shape. So here I'm using a netcdf file that's hosted on the ESGF. I'm sending a request to the server to compute the average over this polygon, so the Colorado region. And what I get is basically the link to the URL storing the data on the server, and I can download that data as well and just display it. This is basically the steps. So you see, open the client, define which netcdf you want to operate on, launch the average polygon process, which looks like a native Python function, but in reality is a remote process that you call using HTTP requests. And then you get the output and display it. And in a nutshell, that's the infrastructure. A data layer, a scientific layer based on the scientific libraries from the Xarray ecosystem, and then a service layer that uses OGC standards with the Python client and server implementations, and basically brings all this science together in something that's fairly easy to use for end users. And so the idea is to be able to connect those different services together to create workflows and let end users that don't have a whole lot of climate expertise or compute storage or CPUs available to run those analyses on our own infrastructure. And yeah, that's what we're doing. And I'm really excited to discuss this with you, answer your questions, and see if there is any way we can collaborate and yeah, see what's going to come out of this. So that's it. Thank you.
Awesome. Thank you very much. So we can, Julius, we can turn off the recording.